Uh, a very warm good evening, everyone. I'll just wait for a couple of minutes and then start the class just to check if someone is joining or not. So I'll share my slides first. Okay. A very good evening, everyone. So welcome you all to the ninth week of the impedance course. So presently we are dealing with mass transfer based like till seventh week we saw what will happen only if kinetics play a role, and then from this week on, like the previous week onwards, we started to see how will mass transfer also affect the rate of the reaction. So how kinetics and mass transfer will interplay is what we looked into. So yeah, my name is Sri Lakshmi. I'll be the taking today's tutorial. And yeah, so last week I just discussed two assignments and some what was taught last week. So that I gave a small introduction, I mean summary, and then moved on. So someone had asked me if I can show the derivation also of um, the mass transfer, that is the semi-infinite and the finite boundary layer. So I thought, okay, so I thought if time permits, I'll also discuss assignment 2 with you. So if that is also complete, I think then as up to assignment 6, we have discussed everything. So yeah, that is the next part. So today I'll start with derivation, as someone had asked me. So yeah, I think so. The topic is diffusion effects. I hope my slides are. So as I mentioned earlier, like up to two classes before, you were seeing the case only when kinetics plays a role. That is, there is no effect of mass transfer. So what happens? Like you have an electrode which is immersed in an electrolyte, and what you're actually saying is some reaction is happening, like A is getting converted to B on the surface of the electrode. So we do this with the assumption that you have A in the solution, so it is getting converted into B, right? So when you do this, we are actually assuming, only context is playing means, we assume that the concentration of A in the solution is so much that it is easily available for the reaction to happen, or it's easily getting converted to B on the surface of the electrode. But in the real systems, is it always the case? Is there enough quantity of A to sustain the reaction? Kinetic reaction, is there enough? So if not, then the mass transfer effects come to play. So that is the case we are looking into. So up to 7 weeks, what we were seeing is there is enough concentration of A for the reaction to happen. But now the case we are going to look into is no, there is no enough concentration of A. So basically you have an electrode. When it is immersed in the electrolyte, in the bulk the concentration will be say bulk, but As you move towards the surface of the electrode, the reaction is fast enough and there is no much A available. So that means here you have some amount of concentration, and as you move towards the surface, the concentration of A decreases. Similar, so this is what is the case you're looking into. So the concentration of A on the surface will be something like CAS or something. Basically, CAS, that is the concentration on the surface, will not be equal to concentration of the A in the bulk. So that means as the reaction progresses, the concentration of A also keeps changing. The same is the case here. So here I can say Ca equal to Cas equal to Ca bulk. So where the concentration of A is remaining the same everywhere, while in this case the concentration of A keeps changing. So that is what is the case you're looking into. So when mass transfer comes into play, the concentration of this reactant on the surface is different from that in the bulk. So there is a variation. So this one is known as a boundary layer. So boundary layer, and you have a thickness for that boundary layer. This is a boundary layer. So this boundary layer can be any value between 0 and infinity. That means it depends upon how the solution is. So if in case you don't provide any stirring, that means you have no stirring, there will be concentration gradient across the what to say, the electrode electrolyte. You will see a gradient across the electrode electrolyte. In case if I provide some stirring, what I'm actually providing an external force by which the A can diffuse onto the electrode surface. So again, in that case, the thickness can reduce, the boundary layer thickness can reduce. So basically, it all depends upon whether you're providing a stirring or not. In case when you're not providing stirring, you have a mass transfer, I mean there is a concentration gradient of A across the electrode electrolyte interface, and that thickness of that can be as high as an infinity. That means there's a huge value, or it can be small value if you're providing enough stirring. Okay. Yes. So yeah, so that was what is the cases we are going to look into. We'll see two cases. One is semi-infinite. That means when you're providing semi-infinite or finite. So these are the two cases you're going to see. Okay. So we'll start with the derivation. Yeah. So you know derivation is lengthy. So today I'm planning to cover the derivations. Okay, so in this part only we had also discussed in the last case about the rotating disk electrode. So if I want to overcome the concentration gradient, I can provide some kind of rotation. So when the speed of the rotation increases, again I'm forcing the reactant to move towards the electrode surface, and I'm promoting the reaction. So in there we again saw the RDE. How do you calculate the boundary layer thickness, and it's nothing but is 1.61. This is the diffusivity of the reactant. So dA raised to 1 by 3, and it is into omega raised to minus 1 by 2 into gamma raised to 1 by 6. So which is the kinematic viscosity. So here you know this is the diffusivity, right, in the unit centimeter square per second, and this is the rotational speed. In centimeter per second. Sorry, radians per second. As mentioned, the units are very important because that is based on these particular unit that the value 1.61 is calculated. and this is the kinematic viscosity. It's a centimeter square per second. So yes, at higher RPM, as RPM increases, you'll see that the boundary layer thickness is reducing. So mass transfer effect will be lower. Okay. Yeah. So this is just the introduction or background of what is being taught. So we'll start with the derivation number 1, and that is for finite boundary layer. Anyone has any doubt in what was written in the last slide? So yeah. So I'm taking a simple electron transfer reaction. Simple electron. For a simple electron transfer reaction, that's like ferrophore. So it is something like A given B plus E minus. So that's the reaction. So you should know a few things. So the first thing is, what is the formula for IF? So I'm saying the forward reaction rate is K1 and backward reaction rate is K minus 1. So IF equal to F K1C and X equal to 0 minus K minus 1 CB at X equal to 0. So here, see, till now we never mentioned if it is X equal to 0 or X equal to some other value. Why do we mention over here? So like usually we write N into F into rate. So why am I here specifically saying CA at X equal to 0, CB X equal to 0? Anyone? So when we are dealing with kinetics, we were telling that the concentration remains the same everywhere. Like there is no uh, change. So we know the reaction happens at the electrode surface. So now that's not the case. The concentration keeps changing, and we cannot say that at the surface the concentration is Ca bulk or Cb bulk. Instead, that value here is Ca at x equal to 0 or Cb at x equal to 0. Right? So that's why we mention in specific. Now what happens at equilibrium? So at equilibrium we know forward rate of reaction equal to backward reaction. So K1 becomes what? It is at equilibrium. So no reaction. So K1 dc e raised to B1 edc, say at x equal to 0. Sorry. What is C1 at x equal to 0? So because at equilibrium what happens? We say that at equilibrium what is happening? So you have enough quantity of A is available. That is, the bulk concentration will be same as that in the electrode surface at equilibrium. Okay. B minus 1. And at equilibrium, that means there is no potential applied. So EDC value will be nothing but 0. So this entire term will be equal to 1 and this will also be equal to 1. So finally what do I get? Finally I'll get something of the form given DC equal to CB bulk. So this is the condition at equilibrium. Then you should also know what is the B1 and B2. B1 is nothing but it is alpha NF. So you know what all are. Sacks-Lanzmann coefficient, number of electrons, Faraday's constant by RT. B minus 1. So these are the basic equations you should know to solve this. Okay. So the main point here is that the concentration keeps changing, okay, on the surface with time as the potential is changing. So the difference is when you're dealing with only kinetics limited, it's only the kinetics, the potential which keeps changing. There is no effect of the concentration change. But when it comes to this case, sorry. When it comes to this case, what happens is along with the potential change, here you will also see that there will be concentration change with type happening. So, this what is there. Now you should also see what's the difference between kinetics limited and kinetics plus mass transfer for a simple electron transfer reaction. Okay. So that's the next thing. So for a simple electron transfer reaction, that is just wait. Yeah. So the reaction is A given for a simple reaction like this. What do you expect? If it was this one, you will expect something of this kind, right? So here you have what is the relationship between RT and RP? Is RT greater than RP or RT smaller than less than RP? Anyone can tell? For a simple electron transfer reaction.
Both seems to be equal.
Yeah, both are equal. So this is our solution. So here this RT plus RT equal to RP at this point. But when it comes to this thing, that is the mass transfer limitations come to play, instead of one loop, you can expect two, okay, at the same for the same conditions, and you will see that RT is not equal to RP. So that's one thing you should keep in mind. And so, like, what does this mean? So you change this circle. That's the first one. So first one is because of the electrode electrolyte interface. You'll see the CDL. I mean the double layer. So because of that, you will have a loop. So after that, it can go like this. When you change the potential, again this one will overlap for a different potential. Again this one will go somewhere like this. So basically if you try, this one will be something like this or something like this, or again the third one at a different potential, you can see it is going like this. Okay, so this one is known as the semi-infinite. So what does that mean? So semi-infinite boundary condition is a case when you're not giving any stirring. So no stirring, or it's a stationary, I can say. The electrode electrolyte is stationary, so the boundary layer keeps growing. So that is a case which is semi-infinite. So all this corresponds to the finite boundary. Okay?
Excuse me, you have
Yes.
written RT is not equal to RP.
Yeah.
So that means the first curve inclines. That shows, I think, RT, and the second inclination is RP. Is it like that?
You have to use the
What is
formula.
the interpretation?
So, like in the sense when it comes to kinetics plus
When
mass transfer, you say when omega tends to infinity, you get
tends to
the
infinity,
resistance to chance transfer, and the other one at omega tends to
omega tends
zero.
to zero.
Yeah,
Right.
yeah. So we'll see that in the coming derivation. Okay. So this was just a brief background, and yeah, you also have to see the difference in uh, the impedance, like how will you represent. So only if kinetics is coming, you will have, okay, you will obviously have a solution resistance, and then after that you will have something like this. Okay, this will be the Faraday impedance. So this for kinetics. So now what will happen if kinetics plus mass transfer is playing a role? So in that case, along with the Faraday impedance, okay, you will have the Warburg, so which will be used to model the effects of mass transfer. So this is the difference when you're trying to fit the model. So this kind of equation, they have both what to say, the mass transfer playing a role and also kinetics. So it's actually quite lengthy. So what Sir has showed you is a simple electron transfer reaction, because if multiple steps are involved, or uh, what to say, theta is involved, the procedure remains the same. The only difference is that, I mean, the thing is you are only accounting for mass transfer, hence it becomes more lengthy. You'll take into account the diffusion effects. So let's start with A giving B plus E minus. Okay, so I'm saying the forward reaction has a rate constant K1 and backward reaction has a rate constant K negative 1. So the first one is, how do you write IF? What is IF? What is the current density? The formula is the same as the last time. So how, if it was the only kinetics limited, how will you write? Anyone? So you have F
F
into
F
uh,
into K1 concentration of A at x equal to 0 minus K minus 1 concentration of B at x
Yeah,
equal to 0.
yeah. So this is the equation we will write. Okay. Now, what is the difference? If so, there's the general expression. So, at where? At the surface of the electron. So, as I told, it was at x equal to 0. Now, at x equal to 0, what is the value of A and what is the value of B? So now if it was kinetics limited, oh, that's only when kinetics plays a role, it will be Ca at x equal to 0 will be nothing but will be Ca bulk. And similarly, Cb at x equal to 0 will be Cb bulk. So there's a case when there is no mass transfer effect. So as I told, when mass transfer comes to play, along with the kinetics, you have the that is potential is applied. Potential, I mean, there can be fluctuation potential, and similarly, there can also be fluctuation in the fluctuation in the concentration. So Ca at x equal to 0 in this case will be Ca will not be equal to Ca bulk. Okay, so I am not showing it as Cas. Similarly, you will have Cbs. So both these terms are different from the bulk. So that is the thing you have to keep in mind. Okay, so the first equation, okay, for that reaction,
But just now, what you have written is equal to, na? Ca at x equal to 0 is not equal to Cas.
Cas corresponds to the concentration of A at the surface.
Right.
Okay, you have Cas and Ca bulk also. Bulk is the one which is there like away from that boundary layer, the concentration of the solution actually. But once it comes, reaction increases at the electrode electrolyte interface, the CAS, okay, will be there. CAS is different from Ca bulk. So basically, if reaction is progressing and A is what is getting consumed, CAS will be less than Ca bulk because it is getting consumed. Okay, so because that concentration at the electrode surface is different from that in the bulk, we say mass transfer effects are coming to play. So CAS is the concentration of A at the surface. S over here means surface. Surface of the electrode. What is the concentration? Bulk is the bulk concentration. Okay.
Okay.
So now the next one is IF. So as we wrote, we'll just so finally we understand that this is nothing but, so for a general expression. So this is what I told that. So one condition, this CAS. So irrespective of what case it is, CBS is the concentration at x equal to 0, right, at the electrolyte surface. We have an electrode, we immerse it in an electrolyte, we say this place as x equal to 0. Okay, and you have a boundary layer. Okay, and this is the boundary layer. So this del can vary from what, 0 to finite value, or it can be as high as an infinity. That is the case for semi-infinite boundary layer condition. So that's how it varies. So at x equal to 0, we'll write as CAS or CBS. And here, after at this particular point, I'll write as CA bulk or CB bulk. So this is what we are looking into. So we want to write the general expression for IF. So IF, because concentration keeps varying, we'll write it what to say, we'll just write it as what is the concentration of the reactant or the product at x equal to 0 as the time varies. Given Ca, this is the expression. Now what? So there's a first thing you can expect, like these questions itself can be asked as step by step you will have to do. The next thing is to check in what happens at equilibrium. K1 0. So we said K1 will be nothing but K1 0 B1 EDC. Basically, it is at equilibrium, so only DC current is applied, and see, because no reaction is happening, you are not having any consumption of A at the surface. So I can write as Ca bulk equal to K minus 1 0 e to the power B minus 1 ETC CB1. So DC, this means, sorry, this is at equilibrium, right? So equilibrium, this means what? EDC equal to 0, not applying any potential. So this one will be 1, this entire term will be 1, right? So if I am shortening it and again simplifying it and writing K1 0, say bulk equal to CB bulk. So with this, the next expression. And I'm numbering this as question number 1. Any doubt? So my first question was, what is the current density? We wrote the expression. After that, what will happen at equilibrium? So this expression can be used because all are constants. Okay, see this constant, this constant. So if in case you do not know any one of the parameter, you can be, I think fun question like this was there in the previous week assignment. Yeah, so that's how you find out. Okay, so all are constants. So now the third part is you are trying to write down, like trying to find out a relation. Okay, like how, what is CA and what is CB. So what comes to play? It is a fixed law. Who can tell what's fixed law? Who can tell what's fixed law? So you have the concentration varying as a function of time, which is equal to the diffusivity times dou square Ca by dou x square. Similarly, dou Cp by dou T is equal to dou square Cb by dou x square. Okay, now we are first considering the steady state condition. So what is a steady state condition? What does a steady state means? Anyone? Any term differentiated with respect to time will be zero. That means
Which
what? That variable is not changing with respect to time. It's a constant. Okay,
right.
so that's why when you're differentiating it with respect to time, you're getting a zero. Okay, so if I apply that on both of this, what I'll get? So dou C by dou T equal to 0, again equal to dA dou square C dou x square. So what does this mean? So again dA can also go because that's 0 that side. So again I'm differentiating it once. You get dou C by dou T dou x. Okay, because it's 0 the other side, again it will be 0 plus a constant. So obviously because I'm not differentiating it with respect to an integral, should give me just a variable. So let it be like b. Okay, now again I'm differentiating it with respect to x, so I get c a equal to bx plus a. Right, this clear, right? Now same thing applies here. When I differentiate this,
Excuse me.
yes, tell me.
You have written 0 is equal to dou A, then
Hmm.
square C upon dou C square, x square.
Hmm.
Then
Then your voice is not audible. I mean, I cannot hear you. You're not audible.
you have written 0 is equal to dou A dou square C upon dou x
Huh.
square.
Hmm.
That implies then how you have written dou C upon dou x square is equal to B.
Sorry, it's dou CA by dou X. Not, sorry,
Right.
sorry.
Sorry.
Thank you. Okay, thanks for showing the mistake.
And secondly, in Fick's law, initially you have written dou C by dou T is equal to dA dou square C upon dou x square. How is it coming? Means what is the interpretation of this? Means how you can understand this?
So that's a law which say that the concentration is changing with respect to time as well as you have with respect to the position. So we are just simplifying it into one dimension, that is along the x-axis. So basically, it is something in the form of you know what is the Laplace equation and all, right? So that's a form. Basically, the variable is varying with respect to time as well as the position. So if I'm simplifying it and just saying that it's varying only along the x-axis, that is on one direction. I'm not considering the multi-dimensional variation. I can write it as dou C by dou T equal to dA into dou square C by dou x square. So like
So
it's
here,
also what is?
what is x here?
So x is like the position. So position in the sense you have, I'll just again draw that you have an electrode and you have an electrolyte. Okay.
Right.
So here the concentration is Ca, bulk, right? And
Right.
what I'm saying, as I'm moving on towards a solution, so here it becomes CaS.
Yes. Surface.
Yes. So you have C bulk here and C surface. So C bulk is something like this high, but as it go to the surface, keeps decreasing and it becomes CAS, right? So this there is a change in the concentration along the x-axis or in one direction. But basically, if we are looking into that solution as such, you can have this variation in x direction, you have that variation in y direction, z direction, everywhere, right?
Right.
So we're just simplifying it. So actually, this entire equation is something like you have dou C by dou T will
Right.
have something like dA. You will account for what to say, dou square CA by dou x square. Similarly, you will have something which will account for that in y square,
Yeah.
again something
Right.
in z square, something like that. Okay, and you'll also have some mixed term, dou square ca by dou x dou y, something like that and all. Okay, so it's a
Right.
complex equation. So here we are just taking it in the x direction. Okay, so here when you, okay, now we're talking about the steady state. So steady state in the sense it doesn't vary across the time, and dA dou square ca by dou x square equal to 0, and then I say dou ca by dou, I'm differentiating it once, I'm constant comes as ca equal to bx plus a plus bx. Similarly, if I'm doing that for this equation, I'll get cb equal to cx plus d. So this are the two equations you're getting, and let me number them as 3.
So we are
So
integrating here.
yeah, integrating same like
Right.
this one. Same
Right.
like this one, because there's also of the form dB into dou square CB by dou x square is equal to 0. So when I integrate this, I get something like this. I'll name this 3. Now, yeah, next thing is you need to know the boundary conditions. So this, so boundary condition, this we are looking for a finite case. Okay, so finite case, the first one is at x equal to a finite boundary layer thickness delta. I'll say CA at x equal to delta will be equal to CA bulk, right? At the interface of, you'll see that at delta, x equal to delta, CA equal to CA bulk. So that is going to be a first condition. Now what is the next condition? What is the next condition? So obviously you have an electrode and you have an electrolyte. So we wrote the condition at x equal to del. Now the next condition can be written at x equal to 0, right? So what is happening at x equal to 0? You have A forming B, right? At the interface. So you have the diffusion of A to the surface. A is getting consumed. Simultaneously B is formed. So A will diffuse in and B will diffuse out, right? So that's happening at the electrode electrolyte interface. So because of that, because there is A moving in and B moving out, you have some reaction happening. So because of that, a current is produced, right? So that will be your next boundary condition. That is at x equal to 0, at x equal to 0, you have dA, dou CA, that is the diffusion of at x equal to 0 at any time will be equal to, there will be a counter transfer of B, right? The B that is formed on the surface will also move out. One moves in, the other moves out. At any time. So because of this, what happens? A current is developed. So the current will give rise to a rate. So moving in of one thing, I mean, A moves in and B moves out. So basically there is a current generated, or there is a net transfer of material happening. So IF equal to NF into rate. So IF by NF is nothing but the rate. So it is just explaining the rate of movement of material across the electrode electrolyte interface. That is at x equal to 0. What is the movement? So this is nothing but there's a flux. There's also flux, and which I'm relating it to the current. Okay, the current generator because of that rate. Okay, so that is what are the boundary conditions you have to know. Okay, so these are the boundary conditions. Just keep this aside. Okay, so this you should have know. Just add few more slides. Yeah. Now we already know at x equal to 0, C equal to CAS and CB equal to CBS. X equal to del, you will have something which is equal to CA, the bulk, obviously, because then that's the other side, right? CB equal to CB bulk. And I'm already having this equation. What CA equal to A plus BX and CB equal to D plus CX, right? I'm substituting in that. Okay, that is. I'm saying at x equal to 0, CA will be equal to what? This one will be equal to CS. So I can say A equal to CS, right? Now the next condition is x equal to del. It will be equal to say bulk. So if I'm so what do I get? Say bulk. I'm just substituting that equal to A. I'm just substituting this condition in this equation, the top one. Say bulk equal to A is what? A is already CAS. We found that out. Plus B del. So from that I can find B as CAB minus CAS by del. So same thing goes for the C and D. We also have CB equal to C plus DX.
Excuse me.
Yes,
So
tell
here
me.
instead of A means C is equal to A plus BX. So
Hmm.
instead of A, you written CAS. No?
Instead of A, yes, yes.
Yes.
Applying this
Plus,
boundary condition.
right.
At
Plus
X,
B, and instead of X, you written delta.
I didn't get you. Instead of,
Here CAB is equal to CAS plus B delta that you have
yeah,
mentioned.
yeah,
So that is derived that instead of A, you have written
CAS.
TS, right?
Yeah.
Plus B, and instead of X,
Huh.
you have written delta.
Yeah. Why? Because at x equal to delta, you have CA equal to CAB. So I'm substituting that in this equation. So CA equal to CAB equal to A value is already known, CAS plus B delta. And I'm rearranging and finding B.
Right.
Okay. So now same way I know CB equal to C plus DX. So at x equal to 0, you will know that CB equal to CBS. If you have any doubt, I'll just expand this one and write. So at same thing goes to CA, right? So x equal to 0, CB equal to CBS. So I'll have CBX equal to C plus 0, right? X value is 0. So I already get that C equal to CBS. Now the next one is again at x equal to del CB equal to CBB. I'm substituting that, so I get CBB equal to CBS plus D del. If I rearrange, I'll get D equal to CBB minus CBS by del. So I have D value here, B value here, C value here, and A value here. So I already know CA equal to A plus BX. I found A, I found B. Similarly, CB equal to C plus DX. I found C, I found D. So this is how you found out A, B, C, D. Now what you have to do? What is still unknown? Is this enough? Which value is not known still? So I wrote, I have B, A, everything expressed in terms of CAB, CAS, everything. But I still don't know what is the concentration of the material at the electrode-electrolyte interface. That is CAS and CBS are unknown, which has to be found out. Okay, so I hope that this point is clear. So I have to find out CAS and CBS. So now the thing is easy. I've got an equation, but the unknowns in those equations are CAS and CBS, which I have to find out. Okay. So for that, now we are moving on to the next part. So we applied only one boundary condition, that are just like at the ends, whatever are the values. I'm just applying that I found. Now there is one more boundary condition I have. That is a flux relation to the current. Okay. So which says dA dou CA by dou X equal to dB dou CB by dou X, right? Now, what does this dou CA mean? It's a variation. If I see, I have an electrode and I have an electrolyte. So at this interface, okay, the reaction is A giving B. You see, A is getting consumed. So I have some value of CAB which gets consumed, and once it reaches the surface, it's CAS. Basically, it keeps reducing. What about B? B is something like B is formed over here and it gets reduced as you go over here. This is a variation. So I'm just expanding it. So across that X, what is this X corresponding to? It is del. What is the variation? So it can be something like from CAB value, it is moving to CAS. by del minus dB CBB minus CBS by del. So now what I have to do, I'm expressing it in terms of CBS. Okay, let's find out what is CBS. So in these terms, there are two unknowns. One is CAS and one is CBS. So I'm trying to expand this in form of CBS. So how can I do that? I'm just taking this DB the other
Me,
side. Yes, tell me.
D A dou A and is you have written CAB minus CAS upon delta.
Hmm.
So
Hmm.
that is B equal to that. Earlier it was written B equal to this one.
I didn't
So
get you.
dou means you have written B is equal to CAB minus CAS upon delta. Earlier we have derived
Yeah.
this. B is equal to this
Yeah.
and B equal to CBB minus CBS divided by delta.
Yeah.
So here dou A is equal to how you have written CAB minus CS upon delta.
You see
From
this
where you have
equation?
written?
Yeah, from this equation.
I couldn't get logical sequence means
Okay.
dou A
Yeah.
by then how you have written?
So I want to find out the equation for CA and CB in terms of known variables. Okay. I have now expanded. If I substitute here, what is A value here? Ah. So here you write CA equal to A plus BX. What is A? A is CAS. B is CAB minus CX by del. Do we know
Yes.
CAB? Bulk concentration of A. That will be a known value. It depends upon the electrolyte you're preparing. Right? You'll know the bulk concentration. But will you know what is the concentration of that particular substance on the electrode electrolyte interface? That will be some small value. It keeps changing, right? Like what I meant is you have an electrode which is immersed in a solution. You know the concentration of the solution, right? That is a bulk
Right.
concentration. Will I know what is the value at the electrode electrolyte interface?
No.
No.
How that
Surface concentration changes. So though I found out an equation for CA equal to A plus BX, okay, in that the unknown variable is still CAS. I am trying to find out what is CA. If CAS is also unknown, how can I find out? Right? CA is what I am supposed to find, and if I am expressing it in terms of another unknown variable, there's no point in what I am doing. So I have to find out CAS and CBS. That's clear. I wanted to find out what is the surface concentration. For that, I'm applying the next boundary condition. What is the next boundary condition? I wrote something like this. At x equal to 0, the flux in and flux out are equal. Right, this one, this equation. So that is nothing but dA into dou CA by dou x equal to minus dB into dou CB by dou x. What does this dou CA by dou x mean? Dou CA by dou x means change in concentration of A across a x. What is this
X.
x corresponding to? It is a boundary layer.
Yeah. Boundary layer.
So I am writing that as del. Now dou CA is what? The change in the concentration of A across that boundary layer. What is the change? Changes from CAB to CAS.
Yes. Yes.
Same way I have written this side. So now I am trying to find out an equation for CAB and CAS. Okay. So I am expressing this full expression in terms of CBS. So
Yes.
CBS is
That
going
means
to be,
dou
yes, tell
C
me.
upon dou X is the change in concentration of A with
Yes,
respect to the
boundary
X
layer.
means
Yes, which is corresponding here to the
yeah,
boundary layer. Okay.
boundary layer. Yes.
Yeah. So now I'm rearranging this equation to write CBS in terms of CAB. So how do I do? I'll take this entire thing the other side. So when I'm rearranging, I'll get CBS an expression. Can anyone tell me? Please try that. It's just a one step you have to rearrange and please tell me. Are you able to get this? Are you able to get this?
Yes,
Yes. So this one
correct.
equal expression. So here now CBS is in terms of CS, right? Again, there are one more unknown. I have to solve any one. So now how will I do? This expression, right? The flux dA into dou CA by dou x equal to minus dB into dou CB by dou x has one more term. If you remember, we wrote something like this equal to IF by NF. Okay. So what is IF by NF? What is IF by NF? So we know IF equal to NF into we write something. What is that? What is this? We write as rate, right? That's what we write, right? Forward minus backward or something. The same thing. Here they have just rearranged and said IF by NF, which is nothing but the rate. Rate what? So this we are talking at x equal to 0, right? At that particular point, that is over here. At this point, the rate will be nothing but is equal to the flux of the material. So I'm just taking dA into dou CA by dou x at x equal to 0 and equating it with the rate at that electrolyte interface. Are you able to get that logic? At the electrolyte interface, the flux is related to the rate of the reaction. Okay, so that is what we are going to equate now. So again, if I write what is the rate? This K1 dC Kx equal to 0 minus K1 dC Cb at x equal to 0, right? Now, you know what is this one? This CAS and this is CBS. What is dou CA by dou x at x equal to 0? I can just write that as the change again. dA CAB by del at x equal to 0, so CAS minus K minus 1 dC CBS, right? So now from this one, we already got, I didn't number anything, right? So this is equation 6, 7, I got 8. From 8, I already got a relation for CBS, right? If I substitute over here, the same thing for over here, I'll get a single expression in terms of CAS. Are you able to follow that? So this will be nothing but K1 dC K minus 1DC CBS. So CBS is nothing but CBB plus dA by dB into CAB minus CS. CBB dA by dB by CS. Okay. Now what you have to do is you have to rearrange and find the expression for CAB. Please do it. I mean CAS. You have to find the expression for CAS. Please do it. Please try parallelly. Are you able to do this? You'll have to open the bracket and okay. Now if you see, I'll try to group all the terms which are having CAS. So we have one over here, one over here. Has anyone got any answer? So I'll take this term and this term and group together. I'll take everything else to the other side. Right. See. Are you able to get an expression like this? Anyone? Anyone got an expression, or do I need to wait or move on? So now I got the value for CES, right?
How this step has come? I couldn't understand
Which
this
one?
step last one.
This one? I rearranged.
Yes, this one.
So you understood this last step?
Yeah, up to here I understood this. Up to
Yeah. So there is one term with CAS and one term over here with CS. What is that? This term is also in CS. I took everything to right and one more here. All these terms are with CAS. So that will give me like dA by del plus K1 DC plus K minus 1 DC into dA by dAB on one side into CAS. Other side, you see, I'll have dA by del into CAB, this first term. And again, this one with this second term will go towards the left side. That will give me K minus 1 DC CBB. Again, this term K minus 1 DC into dA by dB into CAB will also go that side. So three terms on the left, these three will come right. I'll take CS down, a common out, and will go down, and I'll get something of this form.
right.
Mm. Yeah. So that's about CAS. So I already told CBS is something like this. CBS is CBB plus DA by DEB into CAB minus CS. So CAB is known. CAS you will calculate from this equation that you have derived now. Substitute, you will get CBS also. So you're finding CAB, CAS, CBS. After that, you will finally find IF, the current. So the current formula we are writing many times. Just to conclude once again, I'll write IF equal to F into K10 to the power B1 ETC. C at x equal to 0 is nothing but CAS, right? The next one is K minus 1, 0, e raised to minus B minus 1, CBS. Okay? So this is the final expression. So all this we were talking about the steady state current. That is, there is no, what to say, AC effect, only DC. So we started with the, if you remember, we started over here, we said the Fick's law and it's a steady state. So with that, we derived everything. So this is for a steady state condition, this entire derivation you get. Now what happens if the time also plays a role, in the sense there is a change in the concentration over time also. So when unsteady state condition, so is it clear up to this?
Yes.
Yes. So now when it comes to unsteady state condition, what is the difference? So now till now we just wrote K1 equal to K1 naught e to the power B1 EDC, something like this. And I wrote. But I'm not taking into consideration the AC term. AC is not considered anywhere. So that's not how we have to. Now when non-steady state comes, we are taking into consideration that with time also the concentration changes. So same like when we, it's basically like you have with the time you're changing EAC equal to EAC not sin omega t. You're giving a small perturbation. So same case is applied for the concentration also. So we'll be expressing that in a similar way as that of EAC. So that is the concept that you are using. And there will be a change in the equations also. So the first one is dou CA by dou T will be equal to dA dou square CA by dou x square. So this no longer 0. This is the first one. And again, IF equation changes. IF equal to NF K1. K1 is nothing but K10 e to the power B1 E. E in the sense both EAC, EDC is accounted for, and concentration of A till now we wrote x equal to 0. But now along with that I'll write it varies with time. Minus. So this is how the expression will be. You have to account for both the time change and the position. Okay. So now how do you move about? So I will be nothing but IF. Okay, IF. That's what I meant. Okay.
Excuse me, here in the exponential you have written e to the power b1e. So here it is not EDC, no?
No, it
It's
is EDC plus EAC.
EDC plus EAC. E means EDC plus EAC. Both.
Yeah, I just wrote like that. So that's nothing but EDC. I didn't want to be specific. It will be sum of. We used to write, right? Then like K1 0 e raised to e to the power B1 into E is EDC plus EAC. Same thing applies here. IFDC plus IFAC. So this, what is this IFAC? It's a small perturbation. So that's how we have we write, right? We're giving a small perturbation. So I'm just representing it in the form of del IF. It's another notation for the AC current. Okay, and we say that, so till now the case is where it is dependent only on E. Which one? So when I'm applying potential, there will be a change in the current. But now in this case, it's an unsteady state, and mass transfer says so. It depends on three factors: E, CA, and CB. It depends on three factors. So now, how do you find out, like what to say? How can I express this IF? So I can say IFAC, which is nothing but del IF. I've just represented it in another form. Okay. I'm differentiating it with respect to all the three variables. So how will I do? Dou IF by dou E. When I'm differentiated with respect to E, concentration of A and concentration of B will be a constant into dE. So basically this is just a mathematical application. Okay. I'm again differentiating it with respect to E. And here the constant will be a constant E. And constant, sorry, this is not E, this Ca. Into concentration of Ca plus constant E and constant A to concentration of Cb. Let me write this as equation number 1. So if I have to find out IFAC, I have to differentiate it with respect to E. I have to differentiate it with respect to C. I have to differentiate it with respect to Cb. So now the question is, what is IF? I can write IF as K1 Ca, same expression which we wrote before, K minus 1 Cp. F. Now what is K1? We have already know how to linearize it. It is K1 dC into 1 plus V1 EXC into Ca. C8 x equal to 0 for a constant time. So here okay, this will be the first time. Steady state is what is shown by, so it is at the interface. We set t equal to 0 and x equal to 0, this value.
At x equal to 0 to S means x
Steady
will equal to
state.
steady state. Okay.
Steady state means time equal to 0. This is the equation. Now I have to find out these three terms. Dou if by dou E at constant CACB and dou if by dou Ca, constant E and Cb, dou if by dou Cb at constant E and Ca. So the first one, what do I get? So I have an F also. F K1 DC. Please try yourself. What is dou if by dou E? You have to differentiate above equation with respect to E. That's all. So this condition is already known. So I won't be writing it each step. I'll just write. See, I hope so. This term will go because it's a constant 0. K1 DC into B1 do E say by do E into CA minus K minus. So this will be the first equation, dou IF by dou E, which will be substituting over here. Now the next one is dou IF by dou CA. So that means it will be just this term. Okay, when you are differentiating this, it is done at a constant E and constant CB. So constant E means what? The potential is a constant, that is it's a EDC, there is no perturbation given. So automatically EAC value will be 0. So when you do it, you will get only KF into K1 DC. Are you able to understand that? Set a constant potential, so EAC value will be 0. So that term goes. Okay, any doubt? Next term similarly, dou IF by dou CB, again it's CA and E. So when you do that, you will get minus F K minus 1 DC. Now the next step is to so now you know what is dou IF by dou E, you know what is dou IF by dou CA, you know what is dou IF by dou CB, right? Now you have to find out DCA, DCB. You already know what is D. It's nothing but EAC. Okay. DCA is nothing like it's same as delta CA, right? And you know how you write EAC. EAC is what? Basically, it's a small perturbation we are giving, and we write it as both the same. Okay, and it's a small change in the AC potential. And how do you write this? You'll write it as EAC naught sine omega t plus 5 if any phase is there, right? Same thing, or I can write it in terms of the polar coordinates. So same thing comes over here. I can write this AC naught e raised to j e plus 5. Phi a, because you are writing for concentration of heat. You are writing this much. Okay. Now what do you need to do? Now you have to find out dCA, right? Del CA. So you know dou CA by dou T equal to dA dou square CA by dou x square and CA is what? It is DC plus CA AC, right? You have an AC term as well as DC term, of which this CAC is nothing but is this term. Right? Now same thing applies for CB. Please ask me if you have any doubt, okay? I'm moving forward with an assumption that you're able to follow what I'm writing. Okay, you got two expressions. Now I'm substituting them to the Fick's law. C equal to CA DC plus CAC naught e raised to j omega t plus phi, that equation. I made a mistake here. By dou x square. You wrote this much. Now what do you do? This is a steady state, so this will go. Similarly, this will go. Right? Won't change with time or with position. Now, one more thing you have to keep in mind is that CAC equal to CAC naught e raised to j omega t plus phi a, right? I'm just separating that and writing e raised to j phi into e raised to j omega t. So all these are constant, right? I can write that as CA naught with a hash at the top j omega t. So this is what I'll be substituting for this CAC. And if I do that, so what is dou by
Hereby, you have not considered e raised to j phi. You have directly taken CA
this
e raised to
entire
j omega.
thing is written as CA naught with a just simple on the top.
Acha. Yes, you have considered this as a constant.
Yes. See here basically it's varying with time with position. So that's not phi is just a phase. It doesn't depend upon the time or the position. Right. So I'm just clubbing it as a constant. Okay. Now what
Right.
happens? What is dou by dou t of CAC? CAC is this one. So now this is what is CAC. So what is dou by dou t of CAC? I'll get, so the first term is a constant, that is CA naught. And the next term e raised to j omega t. If I differentiate it, I'll get j omega e raised to j omega t, right? Now the next term, that is dA dou square CAC by dou x square. So this is the only term, I mean, where, I mean, which is, so e raised to j omega t is not dependent upon, it doesn't vary with time, right? So we take that term, I mean, it doesn't vary with x, right? So we take that out. So we get an equation like this. And from where I can get rid of both these terms. Okay. If I rearrange this, I can write this in the form of minus, I'm dividing the entire equation by dA. So this is in the form dou square y by dou x square minus mx. So this one will be nothing but square root of m, right? So similarly, so the solution for this equation, so m is nothing but, it's not square root, it's m square. Hello?
ये पेपर अभी
This value is m square. So root of j omega by dA. So if I'm solving such an equation, I'll get of the form C is equal to C1 e to the power mx plus C2 e to the power minus mx. So I'm doing similarly for what to say. So this for CA. So same way I have an equation for CB also, right? CBDC plus CBAC, not e raised to j omega t plus 5b. So if I use the Fick's law for B, and if I do the same thing, I'll get another equation also for B. M dash will be root of j omega by dB, and CB will be C3 e to the power m dash x. So these are the two equations you will get for CA and CB. Okay. So now the procedure remains the same. What you have to do? You'll apply the boundary condition. At x equal to 0, you have someone's mic is open. I mean unmuted. Could you please mute yourself? Thank you. So the flux at the electrode electrolyte interface is equal to the net rate, which is IF by NF. This one you'll apply for the one. Okay, so you know that CA equal to CADC plus CAC. CAC is nothing but CA e raised to j omega t. Now same way IF is nothing but IF DC plus IFAC. So this equation, right? So I'm going to write it in terms of the AC terms. So basically this one will be IFAC, this will be DCAAC, which is like the one with the symbol something like this at the top. So both side I'm writing in terms of AC. So how can I write that? dA dou CA by dou X at X equal to 0. And you have CA bar into e raised to j omega t. This is not a function of X, so I can take that out. Which is equal to IF AC by NF. Again, IFAC is what? IFAC is nothing but IFAC naught into e raised to j omega t plus 5. Again, I can club j omega t, e raised to j omega t into IFAC naught, and I can write that as IF by F. So same into e raised to j omega t. So if you see on both sides I have j omega t, I'll cancel. And if I write this, I can write this as dA dou CA by dou X IF by F. Okay, so you got this one equation. Now you also know at X equal to delta, you have CA equal to the bulk concentration and CB equal to the bulk concentration. So these are your boundary conditions. The first boundary condition is this one, which corresponds to at X equal to 0. We just simplified it and wrote in terms of the AC terms. This becomes your second boundary condition. And which is your equation? You have CA A1 e raised to mx plus A2 e to the power minus mx. Right? Now boundary condition number 1. Yeah. So we are looking for the semi-infinite conditions. So sorry, just wait. Yeah. So here I've made a mistake. So we are looking into an infinite case. So yeah. So at we write a condition where at x equal to infinity, what happens? At x equal to infinity or del, what happens? The concentration becomes equal to bulk. There is no variation. No variation in the sense, this means Ca will be equal to 0. Okay. So when I'm applying this condition, that first condition, I'll get A1 equal to 0 and if I say, use that condition and simplify it and write, I'll get something like ACA is to minus MX. So I got rid of A1 equal to 0. Now I have to find A2. Now how will I find? I have another boundary condition, which is this one.
How can we conclude that A1 is equal to 0? That X
So
equal to infinity, CA equal to CA1. Then
this one will be 0. So I'm substituting it. E raised to minus m into infinity. So this term will become 0 at infinity. So this is also 0. So the only possibility is A1 e raised to mx. X cannot be, this term cannot go to 0. Then the only possibility is A1 becoming equal to 0. Okay.
right.
So I simplified it. Now applying the next boundary condition, that is I have to find out what is dou CA by dou x. How will I do? A2 minus m into e raised to minus mx. So dou CA by dou x, okay, d into dou CA by dou x equal to if by x. This one I found out. This one. Now I'll substitute A2 dA minus m e raised to minus x at x equal to 0 is equal to if by f. And once I rearrange this, I will get A2 is equal to if by f dA into minus 1 by m. Now I found out A2, I know A1 equal to 0. So if I substitute this back, this one will be A2 value, that is if by f dA and substituting the value for m, j omega by dA. Now I know what is if dash, so how can I write that? So this is you have to just what to say, you can expand that, right? You can you know what is if. This one will be IFAC not into e to the power minus j omega t. You can write that. Sorry. A2 CA bar is equal to A2 into e to the power minus mx. So I forgot that e to the power minus mx. So m is nothing but j omega root of j omega by dA. Just have to substitute that. So you get this equation for CA. Now same way, you know what is del CA? e raised to j omega t. Now at x equal to 0, you have to find that value, right? What is at the interface? So you will have Ca at x equal to 0 e raised to j omega t. What is Ca bar? You have one term into e raised, I'm sorry, just wait. Yeah, so you know what is Ca bar, this term, right? And you have at x equal to 0, so this term will go, e raised to minus x mx will become 1. So I'm writing this in the next page. Del Ca at x equal to 0 will be nothing but j omega du. Okay. Similarly, del Cb at x equal to 0, you do the same way, you will get it as del if f into root of j omega dB. Now, are my slides visible? Why did we do all this?
Yes, it is visible. Yes.
Yeah. Why did we do all of this? Any idea? Like you found out del Ca, del Cb. Why did we need this actually? Hey, forgot, huh? I know the derivation is a little lengthy. So that's why when someone asked me they want to learn how to do this, I was like, okay, I'll show. See, we started from here. Del IF equal to IFAC, dou IF by dou E into DE plus dou IF by dou CA into DCA plus dou IF by dou CB into DCB. We found out what is dou IF by dou D. You know what is D? That is EAC itself. And then you found out what is dou IF by dou CA, you found out what is dou IF by dou CB. If you don't remember, yeah, this equation you wrote, you differentiated with respect to E, then you differentiated with respect to CA, and then you differentiated with respect to CB. What were the terms left to find out? You had to find out DCA and DCB at x equal to 0. In order to do that, we had to do this much. We applied the fixed law condition and the boundary condition. We finally did this and we found out that del Ca at x equal to 0 equal to del minus del if by f j omega dA, del Cb at x equal to 0 equal to this much. Now, I'll give you a homework. The next part we'll start discussing from the next class. So before that, so we have almost discussed 90% of this derivation. So now the next part is, you know, all the terms, right? Yeah, this is lengthy. Yeah. If no dou f by dou e, dou f, dou c, everything. Okay. You have to substitute everything. Okay. So yeah, you have this one here, dou f by dou e, dou f by dou c is here, dou f by dou cb is here, d is equal to EAC. Finally, you have del CA and del CB. So substitute and you should find out del IF. You will get an expression, and in that you will have EAC in common. Take it out, divide, and finally you will get a ZF. So this is the equation where you will have resistance to resistance to charge transfer plus ZW form where you have ZWA, ZWB. So finally, when you do it, we'll discuss this in the next class for sure. But just try that out. Finally, you're supposed to get in some form like this. I mean, I believe that you have, it's easy, like when you just sit and see it, you might find it easy. But yeah, we've done almost I mean, more than 3/4, I should say, of that derivation. So yeah, just try this out and rearrange it. Just substitution is left. Please try that, and we can discuss that in the next class. That's on the next Tuesday. Should get something of this form. So this one. So yeah, even the next class I'll be mostly focusing on the continuation of this derivation because this week's and the next week is mostly theory based. You don't have much problem or anything to do. I'd gone through the assignments also. It's pretty straightforward. You have two equations, you have to use that. So that's why I thought someone had asked me to do this derivation in the class, so I thought I'll do this. I am sure we'll wind this up by next week. And yeah, so you should get something of this form after substituting. Then from that we'll find out what is RT, we'll find out what is the Warburg impedance, and finally we'll find out what is RP also. Some people had a doubt like how to calculate RP from this equation. I'll discuss that in the next class. Is this okay for everyone? Are you able to follow? If there are no doubts, I'll save it here. I just stopped with the last slide itself. So we'll discuss the rest of the part of this in the next class. Anyone has any doubt?
Yes, in this part it is okay,
Yeah.
but in the assignment, when they are asking imaginary part of impedance and real part of impedance,
Yeah.
so that part, in most of the assignment, that kind of question is coming. But
Yeah.
particularly, I am not in position to calculate that part.
So
Whatever
basically,
they have discussed in,
you get that. I had tried out that question. That's pretty straightforward. Like you have the value for what to say. Just wait a second. Just take it out. I had worked that out. I'll discuss that also because someone had posed a question saying they have few doubts in the assignment. I'm waiting for sir to clarify on that. Then I'll discuss that assignment. If you see the discussion comment box, someone had told. So that formula is pretty straightforward. You have that that is for the semi-infinite boundary condition, right? So you have that equation 1 plus k1 dc tan h m del by root of j omega dA plus k minus 1 dc tan h m del by. You have an equation like that for a semi-infinite boundary condition. Are you following that equation?
yes,
Yeah, so that equation, you
yes,
just have to substitute the value and you will have to, so in that equation, you just substitute, you see in bottom, you have that root j omega dA, dB and all, right? You'll have to simplify. So as I told it, by hand, it's difficult. So what I directly did is I put that entire equation in MATLAB. And when you try to, just write zf equal to 1, you substitute all the values, write minus j omega, and if you put enter, they will simplify it and give as some a plus ib. So you can directly, for the first part, you'll that a value will be your real part, b will be your imaginary part.
yes. But
I
next class, if you just those which are solved assignment which are done. So if you explain step
if
by step, then it will be more easy for me.
Okay. Because someone had asked me if I can discuss the derivation. That's why I did this derivation today. And
Yes.
assignment, if you see in the site, someone had asked some doubt. So I had worked out. I also got some different answer from what are the solutions actually. So nothing has been updated how is the marking. I'm also waiting for the final answer. Then I'll discuss. So anyway, before the session winds up, I'll surely discuss that. But I also want to know the final answer to just check if I have done it rightly or not. Okay. After that,
It's
like
very useful to us.
yeah.
This
So
class is
I've
very useful to me. I have attended
yeah.
all the.
Yeah, I know you
and
are attending from the starting. So I think I've finished discussing up to seventh assignment. No, sixth assignment. Seventh and eighth are pending. So eighth one actually I worked out. So for many of the questions, I'm getting different answer from what is given as a solution. So someone has posted the doubt in the discussion forum also. So I'm also waiting for the confirmation. So once I'll cross check my answers if they're right, because the difference of answer is coming. I'm just waiting for sir to clarify on that. Then I'll discuss my answers just to check if the way I've done is also right. So because my answers are not matching with the solution given there. So after that, I'll also discuss for sure. Okay. Okay, then thank you for joining the class. We'll meet again in the next class. Thank you.